Hi, I'm Michele Pagani. I will present you a joint work with Damiano Mazza. This work is about automatic differentiation in PCF. Automatic differentiation, AD for short in this talk, provides tools for transforming a program F computing a map of a real or complex number to a program grad F computing the gradient of this map, which is the vector here depicted as these arrows, giving the direction along which the function is supposed to increase the most. AD has many applications in optimization problems. A popular recent one being deep learning, where one wants to minimize the loss function of a neural net by using the gradient descent algorithm or some of its variants. For example, in this code, written in PyTorch, which is one of the most popular library for deep learning, we have a function f, which is the loss function of a neural net called model, and not detailed in this part of the code. And we update the parameter of the model along the gradient computation as performed by this backward method, which is implementing the backpropagation algorithm, which is one of the main algorithms provided by AD for transforming f to grad f. Our goal is, however, not to fix on a specific real-world library like PyTorch, but rather to describe AD transformations in an idealized framework, so to be able to prove mathematical theorems about these transformations. In the POPL 2020, for example, we proved in a joint work with Alois Brunel a complexity analysis of a functional version of backpropagation. In the work I'm presenting now, instead, we focus on the soundness. So the question of today is to understand whether grad f computes actually the gradient on f whenever this exists. The idealized framework we will consider is called the real PCF, that is a simply type lambda calculus with as ground type the type of real numbers, some functional constants to deal with reals like addition, multiplication, sign, or whatever function you want on the real numbers, and then conditionals and fixed points, so to have a Turing-complete programming language. Let us give some notation using this talk. We will call program a PCF term f of ground type R as output, which is the type of real numbers, and some free variables also of type R, which will denote the input of the program. This program will compute a function denoted by these square brackets that can be partial in the sense that f can diverge on some of its inputs. Given a vector r of inputs, then the gradient of f at r will be given as the vector of the partial derivatives of f. So supposing that actually r belongs to the differentiability domain of the function. The program grad f given by AD is then a program having the same inputs as the original one, but as outputs it returns a tuple, which Soundness should prove to be equivalent to this vector of partial derivatives. Actually, AD provides mainly two different ways for computing the gradient, so two different definition of grad f, the forward propagation and the backward propagation. The difference is mainly in the way the partial derivatives propagates along the program. Forward propagation goes from inputs to outputs, while backward propagates derivatives from outputs backward to the input. Mathematically, the two programs compute exactly the same gradient, of course, but algorithmically they have different performances. In particular, in a setting with a huge number of input and a scalar as an output, as it is the case for deep learning application, where the loss functions as the learning parameters as input that can be thousands or millions, then the backward propagation is far more efficient, and this is the case. This is the reason why you often see implemented the backward method in deep learning rather than the forward propagation. But from the point of view of soundness, the two methods share the same issues and properties, and so our theorem applies to both of them, and often we will denote both of them simply by this notation. So this talk splits in two parts. In the first part of the talk, I will give some details of the definition of the forward and backward program transformation. With respect to the usual literature on AD, we have the perspective of functional programming, in that sense, not only that our transformations admit functional primitives, but also that they are defined in a pure functional programming style. In the second part of the talk, we focus on soundness, and our main theorem is that AD might do wrong, but this set of errors, that is the vectors where grad f might compute something different from the gradient of f, is actually negligible, meaning that it is of Lebesgue measure 0. So let us start with the first part of the talk. And actually, grad is defined on the top of a more basic program transformation, noted D, both in its forward and backward version. In some sense, a grad read back the gradient out of a richer computation, which is given by this D. And so let us see how D is defined in the next slide. So the basic ingredient in the definition of D is the chain rule that I recall here in this equation. The chain rules defines the partial derivatives of a composition of function out of the partial derivatives of its components. Actually, this rule is not really compositional, as in order to compute this derivative of the composition, you need both the derivative of the components, but also the values of the inner functions h here. So if one wants to turn this rule into a compositional law, which is fundamental in order to have a neat program transformation, you need to transform the basic values of real numbers into a pair of two different data. On the one side, we have the values of these functions, so still real numbers. On the other side, we have a data structure accumulating the partial derivatives of these functions. In the AD terminology, the first part of this pair is called primal, and the second tangent or cotangent, depending on which mode we are adopting. In the PyTorch framework, the primal corresponds to the data attribute of a tensor, and the tangents to the grad attribute. Now, this comparison might be a bit misleading, as I said before, our definition of D is different from the one you get in standard AD and PyTorch, as we are purely functional and statically typed. So in our context, the types of the primals are given just by the ground type of real numbers, while the type of this accumulator depends on which mode we are adopting. In the case of the forward propagation, the tangents are just tuples accumulating the intermediate computations of the gradients. And in the case of the backward propagation, these the types are, how can I say, continuations, returning this tuple of the gradient at the end of the computation. Let us see now how D transform a functional constant of our language. So suppose we have a constant G representing a basic function of the language, so like multiplication, sign, or whatever you have as a functional constant over real numbers of some arity K. D transform G into a pair of two expressions. The first component of this pair is the original computation of G, so nothing changing is changing here. While in the second component depends on which mode we are adopting. In the case of forward AD, it is just an application of the original chain rule. Just now the inner function h and their derivatives are called by using the primals and the tangents associated with the input variables of g that now are transformed into a pair of two data according to the action of d over the variables. In the backward mode, this same computation becomes a continuation, and the cotangents are now functions and not just tuples. Here is an example of this definition over multiplication in the case of the forward and the backward mode of AD. Let us now see how you extend on the other constructs of real PCF, and the extension is extremely sample, as the definition just commutes all the construct of specific to PCF. So, for example, the D of a lambda is just the lambda of the D of an application is just the application of the D of a conditional is just the conditional of the D, and so on and so forth. So this way of extending such a transformation is called sometimes in the literature operator overloading, as for example Wang et al. 2019 publication, while we prefer to use the functoriality principle terminology, as actually it corresponds to define a D as a functor, actually a two-functor, over syntactic category, and to set that this functor preserve the categorical structure given by the PCF operators. Let us remark also that there is no difference in this extension between forward and backward modes. So these modes makes a difference just at the level of the first order functional symbols of the language. Before going to the core of our contribution, which is the Soundness theorem, let me remark about a potential benefit of such a functoriality principle. By the following diagram. So as I said in the beginning of the talk, many deep learning library implements AD transformation even for quite complex programs. So for example, in PyTorch, you can define neural nets and loss functions dynamically by means of programs F that really contains recursion, branching, and other high-order combinators like maps and list iterators, etc. So F can be really expressive as a PCF program. And now, how PyTorch applies AD to such a program? By following this schema. So this schema, sorry. First, it partially evaluated the program to a first-order expression called a computational graph that morally is just a composition of the basic functional constant appearing in F. And then it applies D to such graph, so getting a new program which is called new computational graph, and this time able to compute the gradient. Well, this is a possibility, okay, of applying AD, but actually with this factoriality principle, many other strategies are possible. In fact, we now are able to apply D directly to the high order program F, so getting a new functional program D of F, and then you can that actually, because of the factoriality principle, D of F preserve all the structure of the original program F. So it's very similar to the original program F. It's just that the ground types that the primitives change. And then you can compute the gradient just by evaluating this new program. And of course, you can evaluate it in order to get the computational graph that is given by PyTorch by following this path. But you can now perform a different partial evaluation, so gaining in modularity. But this is another story. Let us fix for this talk on the soundness. So in the case we take an input from the differentiability domain of your function, does grad f computes exactly the gradient of f on this input? That is the question. And the answer is not, or better, not always. Okay, this problem is well known in the literature under the name is due to the conditional, and it is known in the AD literature under the name of the if problem of AD. So let us see an example. Here you have by using the conditional of PCF, you can express the rectify linear unit ReLU, which is a basic activation function in deep learning, corresponding to the identity on the positive real line and to the zero constant on the negative real line. So if now you consider this expression, ReLU x minus ReLU minus x, you can check that it computes actually in a silly way the identity, okay, on the whole domain. So this means that its derivative should be, that is the gradient of this unary function, so its derivative should be the constant function 1. However, if now you apply the grad transformation I give you before, you can check that on 0, the grad transformation computes 0 and not 1. Because actually on this specific input is giving the derivatives of this of the then branch of this conditional, which is a constant, so of gradient 0. So here we have a mismatch between the mathematical notion of derivatives, which are continuous, and the Boolean type, which is discrete. So there is no continuity in jumping from a then expression to an else once in evaluating a conditional. This is actually, from my point of view, the essence which is hidden behind this mistake. Actually, this mistake has nothing to do with our formalization of AD. You can reproduce it in standard AD library. So in PyTorch, for example, here I can reproduce the expression in that way with this statement. And then if you compute the gradient of this expression by using the backward method of PyTorch on the specific input of 0, well, you get that the derivatives with respect to the input of this expression is 0 and not 1. So you get the same error as before. This problem is well known since the beginning of AD, and a private discussion with Permuted and Siskin, we trace back a first discussion of this problem to a PhD thesis in the 70s by Jos Johan. Okay, and the thesis is available at this link. And in this thesis, a very basic first-order language was defined, and the imperative version of AD was given on the top of it. And the most relevant result was then a proof that actually the set of errors that exist, like this one, is negligible. So meaning that it has a Lebesgue measure 0. So from a practical viewpoint, this means that if you compute the gradient on an input taken at random from a uniform distribution and not from a fixed value like 0 here, then the probability of reaching an error is 0. So, for example, in PyTorch, if now you test the same code but on random reals, like with this expression, you get a sample from the uniform distribution on the unit interval, well, you always get the exact answer and not the error. So in the most of the application of AD, you actually do that. So for example, in the gradient descent algorithm for deep learning, you choose the values at random at the beginning of your algorithm or at the beginning of your learning process, and then you compute the gradient of the loss functions on these values. So you're almost sure that you will get always right answers. So the problem now is to understand whether Jost theorem still hold in functional programming. And this is our contribution to try to answer to this question. And at the left, in fact, you have the programming primitives of the original language considered by Jost, which was very basic, which was a very basic imperative language. Essentially, you have memory references, loops, and conditionals. Okay. So here is our main result. Almost everywhere soundness for AD for PCF. This extends Jost theorem in three different directions. First, in the expressivity of the language, of course, moving from first order to functional programming primitives. Second, we characterize the set of errors, called here fail, F for a program F, with a more precise mathematical notion than just negligibility, which is the notion of quasi-variety, and I sketch the definition here, which is ours. So a quasi-variety is a subset of a countable union of zero sets of maps which are not identically zero and which are compositions of the functional symbols appearing in PCF. Okay, so this notion is parametric on the functional symbols in PCF. And then concluding negligibility from a quasi-variety, we need some hypotheses on that must be satisfied by these functional symbols, and this gives us exactly our third improvement with respect to Jost theorem, which is to precisely characterize which are the hypotheses of your language in order to have this negligibility property, which we identify in the notion of forming an admissible clone. So what does it mean, an admissible clone? So a clone is just a set closed by composition and projection. And then a clone is admissible whether all functions are continuous on their domain, and if not identically zero, the zero set is negligible. So it is trivial to conclude negligibility from this definition and this hypothesis. But I want also to underline that these hypotheses here are not at all restrictive, as for example, any set of analytic functions forms an admissible clone. And also, even if admissibility speak about continuity, I have already shown you how the other primitives of PCF, like conditionals, allows to define functions that are not differentiable or not continuous on the whole domain, as for example, max or the rectify linear unit. Okay, so the language is actually expressible enough to define the usual deep learning architectures used today, and even more. So let us conclude by giving some hints in the proof of our theorem, which splits in two parts. In the first part, we prove that the set of errors of a program is contained in a superset of inputs, which is called the set of unstable points of the program. And the second part is to prove that this set of unstable points is a quasi-variety. So since then quasi-varieties are closed under subset inclusion, we can conclude with the main statement. So first of all, let us understand what a unstable point is. So if you fix now a program F, you can partition the convergent domain of this program between the set of stable points and the set of unstable points. So a stable point is a vector such that a vector R, such that there exists a neighborhood of R and a simple term T. Simple means a term without conditionals, neither fixed points, such that T and F behaves in a similar way on the whole neighborhood of R. So behaving in the similar ways means not just giving the same output when fed with the same input, but means also to compute this output in a similar way. So here there is a simulation relation hidden behind the definition, and you can see the details in the paper. Now, by changing the simple term t, you can have you can prove that different points of f are actually stable, but not all of them. And so we call the input vectors of f that does not enjoy this property the unstable point of f. So for example, in the previous expression ReLU x minus ReLU minus x, you can prove that all real numbers are stable except 0. And here you have the two simple terms proving, witnessing the stability of respectively all the strictly positive and all the strictly negative real numbers. But in the paper you can find more involved example like this expression here, having unstable points as the set of unstable points, not just a singleton but an uncountable set, but always of Lebesgue measure 0. Now that we have defined what are the stable and unstable points of a program, we can prove that all errors of AD are in fact unstable points. The proof is by contraposition. So suppose that we have a vector which is stable. Well, you have to prove that grad f on this vector actually computes the gradient. The proof is follows 4 steps. First, you suppose by definition that there exists a simple term t simulating f in a neighborhood of R. This means that actually the function computed by t and the one computed by f have the same gradient at R. And by results of last year, which have been published independently in 3 different papers, you have the soundness of simply type lambda. You have the soundness of AD for simply type lambda calculus. So you have that the grad t actually computes the gradient of t. And then you can lift this computation to grad f by extending this simulation relation between t and f to a relation between grad t and grad f by a tricky syntactical lemma which we call extrusion lemma in the paper. The second part of the reasoning is to prove that this set of unstable points is a quasi-variety, and this is achieved by a logical predicate, which also is not completely standard. In fact, it deals with open terms because we have to suppose 3 variables of ground types, and also because it needs a mathematical notion of complete quasi-continuity, which is necessary for dealing with conditionals. And with these two statements, so fail is it contains on the set of unstable points, and unstable points is a quasi-variety, we can conclude with our main result, which is the almost everywhere soundness of AD for PCF. Let me show a last slide for concluding, giving a list of some of the literature about the last 2 years on these programming language foundations for AD. This list is not at all exhaustive, but it shows already how exciting and productive is this line of research. First of all, I wanted to point out this survey, which is a very nice entry point if you have no knowledge at all of what AD is. Then I wanted to mention these 2 papers that, from my point of view, starts a functional programming approach to AD before the definitions were mainly based on imperative programming languages. Our contribution of last year at POPL, giving a complexity analysis proof of backward propagation for simply type lambda calculus, actually starts from these 2 papers. And these other 2 papers that we mentioned also before deals with the soundness property of ID for simply type lambda calculus. And in some sense, the contribution of today, our contribution, can be seen as an extension of this result to PCF, with the difficulties of conditionals and fixed points that we have detailed before. These two papers also study first-order programming languages with a gradient operator, and they discuss the notational semantics for these languages. And finally, these three papers, two of which are very recent, also deals about differentiability for some languages of real numbers, sometimes also with probabilistic primitives. And these papers shares with us the fact that they speak about properties which holds almost everywhere, and this is because of the presence of the if-then-else operator. However, their approach is orthogonal to ours, as they study the differentiability domain of the functions definable in a language, and they do not consider the soundness of any program transformation. So this ends my presentation. We are happy to discuss more details in the chat and the question time dedicated to this paper. Thank you.